You walk down the street in literally any major city, you look up at these towering structures of glass and steel piercing the clouds, and your brain just processes them as, I don't know, unmovable objects.
Oh, absolutely. It's like a mountain range of our own making.
Right. There's this inherent expectation of absolute permanence when we look at a modern city skyline. It feels invincible, you know,
Mhm.
clean, precise. Like it's the ultimate victory over nature.
Yeah, I think we project our own desire for immortality onto those buildings. When you see a skyscraper, you're looking at the absolute limit of our current technological reach.
Completely. It's just massive.
Right. It represents wealth, density, and just the sheer collective engineering power of the modern era written in concrete and steel. We naturally assume that our generation has reached, like, the pinnacle of structural dominance.
Well, welcome to today's deep dive. If you're joining us right now, our mission today is to explore an incredibly bold premise provided by the sources you've shared with us.
And it's a really fascinating one.
It is. Specifically, we're looking at excerpts from a piece titled The Eternal Strength of Roman Concrete. And the central jaw-dropping claim we are dissecting today is that ancient Roman concrete is structurally outlasting every single modern skyscraper ever built.
Which sounds completely backward.
It does. So, okay, let's unpack this. Because this isn't just, a fun piece of historical trivia.
No, not at all. This deep dive is really a profound critique of modern engineering's longevity. We are taking the structures we consider to be our greatest achievements and placing them on a timeline where they are, quite literally, losing a marathon to ancient ruins.
Yeah, which is just a wild visual.
It really is. And to understand why, we have to move past the whole romantic idea of ancient history and look at the hard science of how these materials actually function under stress.
Right. So let's start with that phrase the sources use, eternal strength. Because
Yeah.
when I read that, I immediately wanted to push back on the word eternal.
Sure, it sounds a bit dramatic.
Exactly. In modern physics and engineering, everything degrades, right? Entropy is the rule. So calling a building material eternal sounds like poetic hyperbole.
Yeah, it sounds like marketing copy.
Right. It's like comparing a modern high-tech smartphone that becomes obsolete and breaks in 2 years to a solid ancient stone tablet. One is advanced, but the other is essentially forever.
That's a really good analogy.
Thanks. But to figure out if it's a literal assessment, we really have to look at how we define strength in this context. Is it just holding weight, or is it the sheer ability to survive time? Because in modern engineering, we generally talk about two kinds of strength, right? Compressive and tensile.
Yeah, and what's fascinating here is how fundamentally different those two concepts actually are. So compressive strength is exactly what it sounds like, the ability of a material to withstand being pushed together or crushed.
Okay, so just pure downward force.
Exactly. If you stack like a dozen elephants on top of a solid block of concrete and the concrete doesn't crumble, that material has incredibly high compressive strength.
And concrete is good at that.
Oh, it's amazing at it. Concrete, whether it's Roman or modern, is essentially artificial stone. It is fantastic at handling compressive weight.
But skyscrapers don't just sit there holding weight. I mean, they get battered by hurricane-force winds, shifting soil, seismic activity. They sway.
Right, you can literally feel them move at the top.
Yeah. And that introduces the need for tensile strength, which is the ability of a material to resist being pulled apart, stretched, or bent. And standard concrete is terrible at this, isn't it?
It is remarkably bad at it, yeah. If you bend a plain concrete beam, it will snap almost immediately. It has very little flexibility.
So modern engineers solved this by inventing reinforced concrete. We take a grid of steel bars rebar, and we pour the wet concrete over it. So the concrete handles the crushing weight, and the flexible steel skeleton inside handles the bending and pulling.
Spot on. And that combination is the entire reason the modern skyline exists. Without steel rebar, you just cannot build a 100-story tower.
It would just snap in the wind.
It would snap in the wind, exactly. But that exact solution, embedding steel inside concrete, is the fundamental compromise baked into the DNA of how we build today. We basically traded long-term permanence for vertical height.
Because steel has an Achilles heel, it rusts.
Yep, it's highly reactive to the environment.
So modern reinforced concrete is kind of like a cast around a broken arm, right? It's strong, rigid, incredibly supportive. But if water gets inside that cast, the whole environment degrades.
That's a gross but very accurate way to put it.
Mm.
Concrete is naturally porous. It's full of tiny little holes.
Right.
So over decades, rain, humidity, groundwater, all of it inevitably seeps through those tiny pores and eventually reaches that internal steel skeleton.
And when steel rusts, bad things happen.
Really bad things. When it rusts, it undergoes a chemical reaction that causes it to expand up to 4 times its original volume.
Wait, really? 4 times?
Up to 4 times, yeah. So imagine a steel bar locked inside a solid block of concrete suddenly swelling up like that. It generates thousands of pounds of internal pressure per square inch.
Wow. And the concrete just can't handle that outward force.
Not at all. It can't contain it. So it begins to crack, splinter, and eventually it just blows apart from the inside out. In engineering, this is known as concrete cancer or spalling.
Concrete cancer. That is, wow, that is grim.
It is.
So the very skeleton that gives the skyscraper its strength is actively destroying the building from the inside out. That means the moment you pour modern reinforced concrete, you essentially start a ticking clock.
You do. It is a brilliant material for a localized window of time, maybe 100 or 200 years, if you have constant, expensive maintenance. But fundamentally, it is structurally doomed to self-destruct.
Okay, so if we connect this to the bigger picture, you start to see the universal truth about why the sources claim ancient Roman concrete is outlasting our buildings. The Romans didn't use steel reinforcement.
No, they didn't have it. So they relied entirely on the massive compressive strength of their concrete. They designed structures like the Pantheon, which, by the way, still boasts the largest unreinforced concrete dome in the entire world after 2 millennia.
2,000 years. That's just wild.
It's incredible, and they did it by using geometric shapes,
Right.
arches, vaults, domes, shapes that direct all the force downward into pure compression.
Okay, but wait. If Roman concrete is so incredible and it doesn't rust, why don't we just use their exact recipe today to build our skyscrapers? Like, what's stopping us from just pouring Roman concrete and skipping the steel entirely?
Well, because without that steel rebar, Roman concrete still lacks the tensile strength needed for verticality.
Oh, right, the swaying.
Exactly. You cannot build a skyscraper out of unreinforced Roman concrete. The wind shear would just tear it apart at that height. We chose to build high, and to do that, we had to accept the vulnerability of steel.
So we compromised.
We did. The Romans chose to build wide, heavy, and permanently. But, the lack of steel is really only half the equation here. The true genius of Roman concrete actually lies in its chemistry.
Right, and here's where it gets really interesting to me. Because even without steel tearing it apart from the inside, a concrete structure still faces the elements, right?
Right.
Rain, wind, freezing temperatures, salt water.
All the stuff that wears rocks down over time.
Exactly, and modern concrete is a static material. Once it cures, that's it. It's as strong as it will ever be. So when a crack forms from shifting ground or weather, water gets in, it freezes, it expands, and the crack just gets bigger.
Yeah, it's a one-way street toward degradation.
But Roman concrete is fundamentally different. The sources say it's a dynamic, active material.
Yes, and this is where the sources get into the specific ingredients the Romans used. It was primarily a mixture of volcanic ash, which they called pozzolana lime, and seawater.
Okay, so how is that different from what we do today?
Well, when you mix modern Portland cement, you use fresh water, and the goal is to create a completely uniform, chemically inert paste. You want it perfectly smooth.
Right, a homogeneous mix.
But the Romans didn't do that. Their mixing process actually left these tiny, unreacted chunks of lime scattered all throughout the concrete. They're known as lime clasts.
And for a long time, modern scientists thought these white chunks were just evidence of sloppy, ancient mixing techniques, right?
Oh, absolutely. We totally looked down on it. We assumed our modern, hyper-precise, computer-monitored mixing plants were infinitely superior to, guys in togas mixing rubble with shovels.
We thought they just couldn't mix it properly.
Right. But it turns out those lime clasts are actually the secret to the material's longevity. It creates a literal self-healing mechanism.
That blows my mind. So Roman concrete is more like the human body itself. Like when it gets a micro crack, it actually heals its own wounds.
It pretty much does. This is the chemical process known as the pozzolanic reaction.
Okay, walk me through that. How does it work?
So when a microscopic crack inevitably forms in a Roman structure, whether that's from an earthquake or just centuries of ground-settling rainwater or seawater finds its way into that fissure.
And in modern concrete, that water spells death.
Exactly. But in Roman concrete, that water hits those little unreacted chunks of lime. The water dissolves the calcium in the lime, creating this calcium-rich fluid that flows right through the crack.
It acts like blood flowing to a cut.
Yes. That's a perfect way to visualize it. That calcium-rich fluid reacts with the surrounding volcanic ash, and it crystallizes into calcium carbonate.
So it literally grows new rock inside the crack.
It grows new rock, it stitches the fissure shut before it can spread, it essentially scabs over, and the structure actively repairs itself.
That is just, water, the very element that destroys modern reinforced concrete by rusting the steel and freezing in those static cracks, is the exact catalyst required to make Roman concrete stronger.
It uses the enemy as fuel. Look at the ancient Roman harbors along the Mediterranean coast. They have been battered by crashing ocean waves and completely submerged in corrosive saltwater for over 2,000 years.
And instead of eroding, the seawater, filtering through the piers, has spent 2 millennia triggering that chemical reaction. The sources mention it grows rare, interlocking minerals, tobermarite and phillipsite, I think deep within the concrete matrix.
Yeah, those minerals lock together and make it incredibly dense. The concrete is physically harder and more structurally sound today than the day that Roman engineers poured it.
It completely flips the paradigm of structural degradation. Modern concrete begins dying the day it cures, but Roman concrete continues living, reacting, and fortifying itself based on the environmental damage it takes.
And that right there is the eternal strength the sources are referring to. It is not hyperbole.
It's literal.
It's a literal description of a material that thrives on the passage of time.
Wow. Which brings us to the sheer absolute nature of the source's thesis, because it doesn't say Roman concrete outlasts most modern skyscrapers. It uses the uncompromising word every time. Why ancient Roman concrete is outlasting every modern skyscraper ever built. As a listener visualizing their city, that means the Burj Khalifa in Dubai, the Freedom Tower in New York, the Shard in London.
All of them.
The structures we built literally yesterday using supercomputers to analyze every single stress point and wind vortex.
And this raises a really important question about how we define progress. We equate progress with height, efficiency, and usable square footage. We build these incredibly light, flexible, towering structures that generate massive returns on investment.
Because land in cities is expensive, you have to go up.
Right. But we do it using a material system, reinforced concrete, that inherently possesses an expiration date.
We are essentially building disposable monoliths. The Burj Khalifa is an engineering marvel, absolutely. Nobody's denying that. But in 200 years, the steel inside its foundation and core will be fighting a losing battle against the very moisture in the air.
It's inevitable. Meanwhile, the Pantheon has been sitting in Rome for nearly 2,000 years, utterly unfazed.
Just hanging out.
Just hanging out. And the contrast is deliberately meant to shock you. By specifically targeting every modern skyscraper ever built, the sources strip away the illusion of modern permanence.
We look at a skyscraper and we see human immortality.
But the Romans looked at a massive, squat, unreinforced dome and built actual structural immortality. We have the technology to build structures that last thousands of years, but our current economic and architectural priorities simply do not value chronological strength.
We value the view from the penthouse.
We traded the eternal for the spectacular.
We really did. And frankly, knowing the mechanics of how concrete cancer works, you look at a skyline differently now. You don't just see a triumph of engineering, you see millions of miles of steel rebar slowly rusting inside their concrete casings. You see a temporary installation.
It requires a massive shift in perspective regarding our own legacy, doesn't it? We live in a society built on upgrades. The newest phone is the fastest, the newest car is the safest, so we naturally project that bias onto our built environment.
We inherently assume the newest building must be the most durable.
Exactly.
So what does this all mean for you listening right now? Let's distill the core takeaway of this deep dive. The sources present a staggering, scientifically backed reality. The self-healing dynamic chemistry of ancient Roman concrete fundamentally outpaces the static, self-destructive nature of modern reinforced skyscrapers.
It really challenges that deeply ingrained bias that newer automatically means superior.
It does.
It forces us to recognize that progress is not a straight upward line. Sometimes, in the pursuit of one capability, like reaching the clouds, we actively discard mastery over another, like surviving the millennia.
Right.
The gleaming skylines you walk beneath are highly functional, breathtakingly impressive, but ultimately, they're fleeting. They're on a timer.
It really humbles the modern ego. You realize that despite all our computational power, the ancient world solved the problem of time in a way we simply haven't matched in our modern urban planning.
They really figured it out.
They did. Which brings me to a final thought I want to leave you with today. We started by picturing that glittering modern skyline, the ultimate symbol of our era. Right. If their underlying chemistry guarantees that ancient Roman concrete will outlast the rusted, compromised foundations of every modern skyscraper we've ever built? What will the archaeological ruins of our world look like in 1,000 years?
That's a haunting question.
When future historians try to study our era, will the skyline of New York or Dubai have completely crumbled into dust, leaving the ruins of ancient Rome as the only thing still standing to tell the story of human ambition?